This is a 50-tooth combination blade. According to internet wisdom, it's not suitable for heavy ripping on table saws less than 3 horsepower. My table saw has a 1 1/8 horsepower motor, and according to that same internet wisdom, that problem can be solved by switching to this thin Kerf 24-tooth specialty ripping blade. Or can it? Let's find out. In my first video involving blade kerf performance, I looked at cut quality and wood loss. I'll leave a link to that video in this video's description. This time I'm going to look at table saw performance while making heavy rip cuts through 7 different species of wood. I've got my test blank ready to go, and I'm putting the final touches on setting up the table saw. For 99% of most of my cuts, I normally use this Forest Woodworker 2 full kerf blade. This blade works well for ripping up to 2 inches. And since I'm cutting 2.5 inches and some of this is hardwood, I've switched to this full kerf combination blade. And in the background you can see the tachometer. I have the tachometer clamped to one of the floating tables. Then I'll take the little clamp and turn on the unit. And you can see the red light shining down on that auxiliary spindle on which I've taped a piece of reflective tape. For those who aren't familiar with Shopsmith, I turn this crank and I'll turn it up to saw joint R. According to my Shopsmith Mark V quick reference, general sawing for both hardwood and softwood is letter R. And according to the reference chart that I've printed out, speed R should be about 3,500 RPM. You'll notice that my quick reference chart is recommending speeds N and O for heavy ripping. So why did I choose R instead of N or O for this test? Well, I have a technical explanation for that. Don't worry, there'll be pictures. Many table saws on the market today use a 2-pole 60 Hz induction motor which spins at 3,450 RPMs. For example, if we look at the specifications for the Delta 36-725 T2, it has a direct drive motor system which lists 3,450 RPMs as the speed, and elsewhere in the specifications refers to 3,600 RPMs. My Shopsmith headstock also uses a 2-pole 60 Hz electrical motor which operates at 3,450 RPM. But it is also connected to a variable speed belt drive system that changes geometry as I turn the crank on the headstock. When the speed dial is set to letter R, the pulley system creates approximately a 1-to-1 ratio between the motor drive and the spindle shaft. In this configuration, I'll be emulating very many table saws on the market today. So hopefully the way I have this set up, you'll be able to see me cut the board and monitor the RPMs at the same time. The first task though is to square up the sides of the board so that all the samples are the same length. My next step is to glue my test pieces back together again and then run the tests again with this thin Kerf CMT specialty ripping blade. Looking at the minimum and maximum RPMs showed that the full Kerf blade spun slightly faster during cutting softer woods, while for the most part the thin Kerf blade spun slightly faster while cutting hardwoods. But it's not a tremendous difference. It's worth noting that I did get significant bogging while cutting the pine sample with the thin Kerf blade. I'm not sure what happened there. That's pretty uncharacteristic in my experience. I think there was just a bizarre situation with the sample boards that I had put together. Since the minimum and maximum RPMs don't give us a definitive judgment on which blade is better for my table saw, I took the delta between the minimum and maximum and plotted it side by side with the cut duration, meaning how long it took me to move the workpiece through the cut. Now I did try to maintain an even cut speed, but you'll see from the numbers I wasn't exactly successful. I think what I was doing is instinctively changing the feed rate based on the feedback I was getting from the table saw. This view of the data is sort of the same thing. The full Kerf blade did slightly better with the softwoods, and the thin Kerf blade did slightly better with the hardwoods, but in either situation, not very significant differences. I'm going to try one more look at the data by combining the cut duration and the delta between the minimum and maximum RPMs into one single normalized value. And except for the pine sample which bogged down the thin Kerf blade, which I don't think is representative anyway, there really isn't much difference here. In some cases, the thin Kerf blade performs slightly better, and in other cases, the full Kerf blade performs slightly better. Also, I use this infrared thermometer to take temperature measurements in 3 specific locations before making all the cuts and then after making all the cuts. I did this for both the thin and full Kerf blades, and the average temperature increase was about the same. This is a specialty ripping blade, this is a combination blade, this blade has 24 teeth, this blade has 50 teeth, this is a thin Kerf blade, this is a full Kerf blade. According to that internet wisdom I talked about earlier, this blade should have kicked this blade's butt, but it didn't. They're about the same. The average cut duration on the thin Kerf blade was 35 seconds, and the average cut duration on the full Kerf blade was 32 seconds. Throwing out the bizarre pine sample, this blade on average slowed down in the cut 290 RPM. This blade slowed down in the cut on average 325 RPM. That's only a 35 RPM difference. But the cut quality with this combination blade was far superior to this blade. So even though my table saw provides far less than half the 3 horsepower recommended for full Kerf blades, I'm happy with the performance of these blades, and these are my go-to choice for all cuts. Well, that does it for this woodshop nerdery video. I hope to see you next time.